Hello there, Mr. Sutton here, bringing you the AB Calculus 4.8 Extra Practice Number 4 Solutions on Mean Value Theorem. For this problem, we are given the curve 2 parentheses x minus y equals 3 plus cosine of y, and we're also told that for all points on the curve, the derivative is somewhere between 2/3 and 2. So based off of this, the first part of this problem just wants us to show that the derivative equals 2 over 2 minus sine of y. So since y is difficult, well actually impossible, to isolate in this problem, we're going to have to use implicit differentiation. But to make my life a little bit easier, I'm going to start by at least distributing this 2 here. I mean, why leave that in the parentheses? So this is going to be 2x minus 2y. And now implicitly differentiating from left to right, 2x derivative is going to be 2. Negative 2y, that's going to be a derivative of negative 2 dy over dx. Remember, anytime we take the derivative of something with a y is really an inner function of x, so we have to multiply by the derivative of y using the chain rule. And then over here, 3's derivative is just 0. Cosine, that's going to be negative sine of y, dy over dx. And now we're just going to get the dy over dx's on one side and the non-dy over dx's on the other side. So this negative 2 dy over dx can stay where it is. And I'm going to add the sine y dy over dx to be over there as well. And then let me just subtract 2 to get it over to the right side. Now that I have only dy over dx's on the left side, I can factor out a dy over dx, leaving me with negative 2 plus sine of y inside. And if I divide both sides by that, well, I mean, this is really just sine of y minus 2. Or actually, I'm just going to leave it the way it is. I'm tempted to turn things around because I see here that this 2 is positive in the answer they're looking for, but I'm just going to divide by everything the way that it is. So we've got negative 2 over negative 2 plus sine of y. And the reason I'm going to just keep things the way they are is because I recognize that I can multiply this whole fraction by negative 1 over itself to get 2 over 2 minus sine of y. And that is going to match the exact answer that they were looking for. For this part of the problem, for negative pi over 2 to pi over 2, they're telling us there's some point P on our curve such that the tangent line has a slope of 1, and they want the coordinates of this point. Well, we already have an equation for the tangent line. From part A, that was 2 over 2 minus sine of y. So we just want to figure out where this thing equals 1. Okay, well, let's solve for y at least. There's only one variable, so that's good. So I can multiply both sides by 2 minus sine of y. That gives me just 2 equals 2 minus sine of y. And then if I subtract 2, I've got 0. So I've got negative sine of y equals 0. So this is the same as sine of y equals 0. So where does sine equal 0? On the interval from negative pi over 2 to pi over 2? Well, there's only one spot, and that is at the y value here, 0. So that at least gives us a starting point. But to get the rest of the point, how do we do that? Well, we have to go back to the original equation where x and y have a relationship and actually plug 0 back in here. So I can write 2 times x minus 0 equals 3 plus cosine of 0. And just simplifying this a little bit, on the left side, this is just going to be 2x. On the right side, we've got cosine of 0, which is 1, so this is 3 plus 1. And if 2x equals 4, that means x must equal 2. So then we have the point 2, 0. On this problem part, they want us to determine the concavity of the curve at the points between negative pi over 2 and pi over 2, at least for y values, and of course give a reason. So for this one, let's first go back to that part A first derivative that they gave us. So again, that was 2 over 2 minus sine of y. If we're talking about concavity, I mean, we may not know exactly what we're supposed to do when we get there, but we at least need to figure out what the second derivative is. And we'll cross the rest of that bridge when we go there. So before I take my derivative, I'm going to first rewrite this as 2 parentheses 2 minus sine of y to the negative 1. That way I can avoid using the quotient rule. And now just using the power rule with a little chain rule built into it, we have negative 2 times all of this stuff to the negative 2 power. So that's the outer rule. But now we have to use the inner derivative. So that's going to be derivative of 2 minus sine of y. and that's going to be negative cosine of y. But wait, we're still implicitly differentiating because we're taking the derivative of y, an inner function of x, so we have to multiply by a tail of dy over dx. All right. So I'm going to simplify and clean this thing up a little before I try to analyze what the concavity is based off of this. So let's see here. We've got a numerator and a denominator. In the numerator, we have, let's see, negative and a negative cancels, so just 2 cosine of y. Denominator, we're going to have 2 minus sine of y quantity squared. And all of this is getting multiplied by dy over dx, which I guess you could put in the numerator if you wanted to, but you don't have to. So now we're trying to figure out whether this thing is positive or negative for y values that are on this interval. Well, for y values that are on this interval, what can we conclude about each part of this? So on this interval, you're between, let's see, this is the bottom of the unit circle, this is the top. You're in quadrants 4 and 1. You're on the right half of the y-axis, which means that cosine, the x value of an angle on the unit circle, cosine is going to have a value that's positive. So this 2 cosine of y expression will be greater than 0 for the interval they're giving us. So we've got one positive here. Now this 2 minus sine of y, I mean, that's not necessarily going to stay positive because you have values above and below the x-axis on this interval of y values. However, you're squaring it. So no matter what happens with this trig function, this denominator is going to come out positive as well. And finally, we have the derivative itself, which counts, has its own value, but they told us up here in the stem of the problem that dy over dx is always between negative 2/3 and positive 2/3. So therefore, it too has a positive value. Since all of these are positive, that means that the quotient and product of all of this stuff, the second derivative, must also be positive. And if the second derivative is positive, this implies that on the interval from negative pi over 2 to pi over 2 for y values, we have a concave up function. Curve, at least. Not necessarily a function, but the curve is concave up. On this last part of the problem, they're telling us that y equals f of x is a function after all, defined implicitly by the function they gave us, or the equation they gave us in the beginning, and they're telling us that it's continuous on the closed interval 2 to 2.1 and differentiable on the open version of that interval. And they want us to use mean value theorem on the interval to show that this relationship holds. So let's talk a little bit about mean value theorem. Mean value theorem says if your function is continuous on a closed interval, like the one they set up there is, and differentiable on the open interval, then the average rate of change along that interval is guaranteed to equal the derivative at some specific place on that interval. So we can say that f prime of c equals average rate of change, which would be, let's see here, f of 2.1 minus f of 2 over 2.1 minus 2. So this has to equal f prime of c for some c value on the interval from 2 to 2.1. Okay, well, this derivative, we actually know kind of sort of what this derivative is. Up here, they said the derivative is always a number between 2/3 and 2. So because we're guaranteed the derivative is between those two numbers, that means that this average rate of change, which equals the derivative, also has to be between 2/3 and 2. So I'm going to basically replace dy over dx with the average rate of change in this inequality, and that's eventually going to lead us to where we need to go with what they said in the problem. Before I do that, though, 2.1 minus 2, that's really 0.1 or 1/10. Dividing by 1/10 is really the same as multiplying by 10. So I'm going to rewrite this as 2/3 less than or equal to 10 times f of 2.1 minus f of 2 less than or equal to 2. So I basically just put in my a-rock in here, but I simplified it so that it was a little bit easier to work with algebraically. All right, now that I've done that, I just want to have this expression in the middle, so I'm just going to divide all three sides here by 10. 2/3 divided by 10, that's really 2 over 30, which is 1/15, which is what we wanted. Over here, 2 over 10 is really 1/5. So this gives us exactly what we were looking for. On this calculator-based free response problem, we're given a twice differentiable function f such that the first derivative at 1 is 0, and the second derivative is given by this formula, but only on -1 to 3. So we want to know on the open intervals contained here, on which of these intervals is our graph of f concave up. So we basically need to know where f double prime is positive. So first, let's figure out where f double prime of x equals 0, and then we'll just take a look at our graph and see where f double prime is above the x-axis. So here I am in my y equals. I've put the f double prime function in y1, and I'm now going to graph that on the interval from -1 to 3. Let me go to window, and we'll do -1 to 3 on that one, and zoom 0, zoom fit. Let's see what this thing looks like. So there we are. Looks like it kind of sort of crosses, maybe, a few times over here. It's kind of hard to tell. So I'm going to zoom in a little bit. I'm going to change my window a little bit so that I'm not going so far out on the y values. Let me go between, say, -3 and +3 for y values. And let me graph that. And it looks like I'm bouncing here. It doesn't look like I'm getting above the x-axis on this one. So really, it's just this spot here and this spot over here at the very end where I'm positive. But let me find those x values now. So there's the graph. I'm just going to draw it over here. And definitely we get a 0 as we go to 0 here, which you can tell. I mean, if you plug in the x value 0, it's going to zero out this whole equation. But now going back to see what some of these other x-intercepts are, if I do second trace, option 2 for zeros, let me click enter a little bit to the left of this 0, and again a little bit to the right. One more time. That's about 1.253 right there. And then moving back to find the next one. So second trace zeros again. Let me move all the way over here now. Enter to the left, enter to the right, enter one more time. That's about 2.171. And then we'll do one more. Second trace zeros. And let's move my spider further still. And where did he go? Oh, there he is. And enter again. Enter a third time. And this is about 2.802. So looking at our graph, it looks like f double prime is positive on the interval from 1.253 to 2.171, and also on the interval from 2.802 to, well, probably more, but we'll just say 3 because that's all they care about. So therefore, that means that f is concave up on these same intervals. For this next part of the problem, they're asking if f has a relative min, max, or neither at x equals 1 with justification. So we don't know a whole lot about f prime, which would tell us whether we had a min or max based on whether we had a sign change in f prime. All we know is that f prime of 1 is 0. So we know we at least have a critical value, and we'll just put that down there for safekeeping. However, we don't know enough about f prime to do more with it. So we're going to have to use the second derivative test. I'm going to just plug the x value 1 into the second derivative, which I already have right here, and we'll just see if this comes out positive or negative. So let me do f double prime of 1 and see what that comes out to. Now, since I've already stored f double prime as y1 on my calculator, I can just do alpha trace and put that 1 inside of parentheses and press enter. So that's going to be about negative 0.540. And most importantly, this is negative, less than 0. So that means that I'm going to have a relative max at x equals 1 by the second derivative test. On this part of the problem, they're asking us to use the mean value theorem on the interval -1 to 1 to show that f prime of -1 can't equal 2.5. So with one of these problems where they're asking you to use a theorem to show that something's not true, it's often helpful to assume that the thing in question is true and see what also has to be true until we reach a contradiction. So let's start with mean value theorem and the conditions for that. Mean value theorem, you need a function that is differentiable on an open interval and continuous on a closed interval. Well, we know that f prime, the function in question, is differentiable everywhere because they said that f was twice differentiable. Therefore, its derivative is differentiable. So we've got that. That was necessary to state here if you're going to be using the mean value theorem. Now, the mean value theorem also states as its conclusion that if we are differentiable on this interval, then the average rate of change of this function, f prime, on this interval is going to equal the instantaneous rate of change of f prime, f double prime, somewhere on this interval. So let's see what the average rate of change would be if f prime of -1 were actually 2.5, because that's a value that we're going to try to show that f double prime cannot equal. So let's assume, again, that f prime of -1 is 2.5. If that's the case, then the average rate of change, which would be f prime of 1 minus f prime of -1 over 1 minus -1, the average rate of change of f prime, this would have a value of, this is, let's see, 0. They gave us f prime of 1, 0 minus 2.5, all over 1 plus 1, which would itself be about, let's see here, -1.25. So if f prime of -1 is 2.5, then this is the average rate of change. So by the mean value theorem, that means that f double prime of c has to equal -2.5 for some c value on -1 to 1. If f prime of -1 really is 2.5, because all the other conditions of the mean value theorem are met. Well, can f double prime of c actually take on this value on the interval from -1 to 1? Let's take a look at f double prime of x. So this is a function that is made up of a product. We have an x squared times a cosine of some stuff. On the interval from -1 to 1, which is the only one we're concerned with, x squared, if you take a number that's between -1 and 1 and multiply it by itself, you have to get another number that's also between -1 and 1. So this part of the function is going to be less than 1 in terms of absolute value. The other part is cosine. Now, cosine, we know, always gives you back a number between -1 and 1, including -1 and 1, but it's going to be at most -1 and 1. So if you take a number that's between these two numbers and multiply it by another number that is at most 1 in any direction, you end up with a number that is between -1 and +1. So that's what f double prime has to be on this interval. Now, the reason this is important is for the mean value theorem to back up f prime of -1 being 2.5, f double prime would have to make it to -2.5, but it can't, you see, because it can't go more negative than -1. So f double prime, we see, cannot have a value of -1.25 on this interval. Well, since f double prime cannot equal a rock using this value of f prime of -1, that means, since all the other conditions of the mean value theorem held up, that f prime of -1 cannot possibly be 2.5. On this problem part, we want to know if f has a point of inflection at x equals 0. Well, to figure this out, let's take another look at that graph of f double prime that we did in part A. So there it is again. You can look at it on the calculator. And for a point of inflection to happen for f double prime needs to have a sign change at x equals 0. Looking at the graph here, before we get to x equals 0, f double prime is negative, and it's also negative after. It just bounces off the x-axis at that spot. So because f double prime does not change sign at x equals 0, therefore we know that f does not have a point of inflection at x equals 0.